Welcome, architects and engineers. Today, we are unpacking a critical concept in modern AI engineering, agent taxonomy in production. We will definitively separate basic, shallow agents from advanced, deep reasoning systems. By the end of this session, you will know exactly how to architect systems capable of solving long-horizon, complex tasks. Let's get started. To architect AI successfully, we first need a shared language. What is agent taxonomy? It is a classification framework that categorizes AI systems based on their reasoning depth and autonomy. The basics move from simple prompted LLMs to hybrid RG, then to shallow React loops, and finally to deep agents. Why does this matter? Because treating a simple chatbot the same way you treat an autonomous software engineer will lead to catastrophic design failures. How do we differentiate them? We look at their execution loops. A basic agent answers a question and stops. A deep agent might run for hours, correcting its own mistakes. In our deep dive, we realize this all boils down to statefulness. The deeper the agent, the more it relies on external memory and persisted state rather than just holding everything in its immediate context window. Look at this high-level evolutionary flowchart. At the top, we have a static LLM, which just predicts text. When we add basic tools and short-term memory, we evolve into the orange node, the shallow agent. But the true paradigm shift happens when we add explicit planning mechanisms and file system access, evolving the system into the green node, a deep agent capable of autonomous, long-horizon execution. Let's examine the orange node from our previous slide, shallow agents. What are they? Shallow agents are essentially smart scripts powered by a React reason and act loop. The basics: the LLM receives your prompt, decides to fire a tool, looks at the observation, and answers. Why do we love them? Because they are incredibly fast and cheap. If you need to route a customer service ticket or fetch a live stock price, a shallow agent is perfect. How it works is a simple, tightly constrained loop, usually capped at a few iterations. But our deep dive exposes their fatal flaw, context rot. If you ask a shallow agent to research a 50-page document, it dumps all the intermediate search results directly into its main context window. Within minutes, the prompt becomes bloated with noise. The AI loses its cognitive focus, and it begins to hallucinate. They cannot scale to complex problems. This diagram illustrates the classic React loop of a shallow agent. The user request enters the reasoning engine. The model decides an action, triggering tool execution. The observation flows right back into the exact same reasoning node. It circles this tight, blue loop until it has enough data to output a response. It is efficient, but because everything flows through one single reasoning node, its memory capacity is strictly limited. When a task takes hours, we must upgrade to deep agents. What are they? Deep agents are robust reasoning systems engineered for long-horizon workflows. The basics: these systems don't just loop, they plan, they pause to ask you for approval, they spawn workers, and they can run for days. Why are they necessary? Because writing an entire web application or conducting a comprehensive financial audit cannot be brute-forced in a single loop. How do we build them? A deep agent requires 4 architectural pillars: explicit planning tools, sub-agent delegation, a file system for intermediate state, and a highly engineered system prompt. In our deep dive, we see how they cure the context rot that plagues shallow agents. Deep agents decouple reasoning from execution. They do not read a massive log file into their brain. Instead, they command a sub-agent to read the file and return a 3-sentence summary. The main agent's mind remains pristine and focused on the ultimate goal. This mind map outlines the 4 pillars of deep agent architecture. From the core, we branch into planning, utilizing dynamic to-do lists. Next is delegation, where the system spins up hierarchical sub-agents with isolated contexts. Then we have state management, replacing raw prompt memory with actual file system access and vector databases. Finally, governance ensures safety through heuristic prompts and human-in-the-loop approval gates. Let's unpack the first 2 pillars, planning and file systems. What does this mean? It refers to how a deep agent tracks progress and stores thoughts without overloading its context window. The basics involve giving the agent tools to literally write a to-do list to a file and update it as it works. Why? If an AI forgets its place in a 50-step process, it enters an infinite loop of repeated actions. How do we implement it? We expose tools that allow the agent to write its current state to disk, like savingplan.md, and we instruct it to read that file on every new turn. In our deep dive, we realize we are recreating classic computer architecture. By doing this, The LLM's context window acts as the CPU cache, extremely fast, but very limited in size. The file system acts as the hard drive, slower to access, but infinite. The deep agent learns to swap data in and out of its cache, giving it limitless operational capability. This architecture diagram visualizes the memory swap. The purple LLM context window functions as the CPU cache. It communicates via read and write tools with the local file system, which functions as the hard drive. The file system holds persistent files like plan.md and intermediate data.json. When the LLM needs to remember its overarching goal, it pulls just the plan file, updates the status, and flushes it back to disk, keeping its cache lean. The third pillar is where deep agents truly scale: hierarchical subagents. What is this? It's the ability for a main orchestrator agent to spawn specialized, temporary workers. The basics: instead of giving one master agent 50 different tools, the master gets one tool, the ability to delegate. Why is this revolutionary? Because giving an LLM too many tools severely degrades its routing accuracy. But a specialized subagent with just 3 tools performs flawlessly. How we do this is by sending a prompt to a worker agent, say a code reviewer, which boots up, does the job, and dies. Our deep dive reveals this as the ultimate cure for context rot. The subagent might read 20 massive files and make 5 tool errors while debugging. Because it operates in total isolation, none of that messy garbage pollutes the orchestrator's mind. The orchestrator only receives a clean, 2-paragraph summary of the solution. Look at this hierarchical delegation flow. The orchestrator agent at the top maintains the main context. It spawns a research subagent and a coding subagent. Notice that both subagents drop into their own isolated contexts, represented by the circles. The subagents perform massive web searches and heavy file reads, absorbing all the token cost and noise. They then follow the bold arrows to return only the clean, synthesized summaries back to the orchestrator. The final pillar that binds the system together is the system prompt and heuristics. What is this? It's the foundational instruction set defining the agent's identity and boundaries. The basics: for a deep agent, you don't just tell it what to do, you must teach it how to think. Why? Because hard-coded if-then instructions break the moment an autonomous agent hits an unpredictable edge case in the real world. How do you fix this? You use heuristics. Instead of strict rules, you provide principles like always choose the simplest solution or always verify your assumptions before modifying a file. In our deep dive, we note that enterprise deep agents have system prompts spanning hundreds of lines. By providing a flexible reasoning framework like identify, gather, resolve, confirm, you empower the LLM to use its natural pattern matching strengths to gracefully navigate unexpected roadblocks without crashing. This flowchart contrasts prompt engineering styles. On the red path, rigid rules like if X then Y hit an edge case, resulting in an immediate system crash or hallucination. On the green path, a heuristic prompt guiding the agent to verify assumptions encounters that same edge case. Because the agent understands the principle, it adapts, queries the data, and proceeds to successful execution. Heuristics enable true autonomy. Let's observe this taxonomy in a highly valuable real-time use case: autonomous issue resolution. The scenario: a critical bug is reported on GitHub. A lead engineer simply comments at Claude, fix this. If we used a shallow agent, it would try to read the entire repository at once, hit a token limit, and guess a generic, broken patch. But because Claude Code operates as a deep agent via GitHub Actions, the workflow is entirely different. First, it reads the issue. Second, it pulls Claude.md to understand your specific architectural rules. Third, it uses grep tools to surgically locate the broken file. Fourth, it spawns an isolated coding subagent to write the fix. Fifth, it runs your test suite, and upon success, creates a formatted pull request. The value is astronomical. The deep agent autonomously manages a complex engineering pipeline, perfectly mimicking how a senior human developer approaches a problem. Follow the sequence diagram of our deep agent in action. GitHub triggers the deep agent. The agent immediately consults the file system to read Claude.md and grep for context, ensuring it only loads what it needs. It then delegates the heavy lifting to the subagent, which returns the patched code. The deep agent verifies the work by running unit tests on the file system, and finally, pushes the polished pull request back to GitHub. Let's conclude with governance and evaluation. Deep agents are immensely powerful, which means they require strict oversight. Always implement human-in-the-loop approval gates before the agent executes destructive actions like pushing code or dropping databases. Next, evaluation. Do not judge your agents on vibes. Use frameworks like prompt flow to evaluate your deep agents against strict grading rubrics to ensure enterprise consistency. Furthermore, be vigilant with cost monitoring. Because deep agents loop autonomously, they can consume massive token budgets if left unchecked. Set hard iteration limits. The evolution of AI is moving from simple task automation to deep, world model understanding. Mastering when to use a shallow script versus when to deploy a deep reasoning system will define the next generation of engineers. I invite all learners to like, subscribe, and visit quicktechie.com for premium certification prep, including massive Q&A banks, full ebooks, audiobooks, full-length training courses, and expert interview guides. Thank you for watching. Our final mind map summarizes the path to production success. From the core, we must establish governance with human-in-the-loop and strict approval gates. We enforce evaluation using concrete rubrics and prompt flow testing. We maintain cost control by setting iteration caps and monitoring tokens. Ultimately, it all rests on making the correct taxonomy choice, deploying shallow agents when you need speed, and deep agents when you require sustained, complex reasoning.